Metal feels colder than wood even though they're the same temperature. Why does that happen? The secret is heat speed through matter. It's faster in metal, but what makes our skin feel it so sharply? Stay tuned to see how conduction rewrites comfort and why your hand shivers. Okay, that was just the surface. Now let's break it down. Heat moves through solids by conduction, tiny particles, and electrons carrying energy from hot to cold. Metals have a lot of free electrons, so they shuttle heat quickly. Wood lacks them, so heat lags behind. That speed difference is why your skin feels colder on metal. When you touch a metal spoon in a kitchen, it feels colder than the wooden counter. The sensation is not because the metal is actually cooler. It's due to how heat moves between your skin and the object. Heat flows from warmer to cooler regions through conduction. The rate of this flow depends on a material's thermal conductivity. Metals have high conductivity, so they draw heat from your hand quickly. Wood, by contrast, conducts heat slowly, keeping the temperature difference between you and the surface smaller. Your skin senses this rapid loss of warmth as a cold shock. Thus, even at room temperature, metal feels colder because it steals heat faster than wood does. This effect is visible in everyday objects like door handles and kitchen utensils. Understanding thermal conductivity explains why we instinctively reach for wooden tools when cooking. Pos 0.8's thermal conductivity tells us how fast heat travels inside a material. It is represented by the symbol K and measured in watts per meter Kelvin. A higher K means heat moves more quickly from hot to cold regions. Metals typically have K values around 200, while woods are near 0.1. Because of this difference, a metal surface draws your hand's heat faster. The equation K equals QL/A delta T links conductivity to the heat flow rate. In this box we see the symbols simplified for clarity. Below, a bar chart shows common metals and wood side by side. Notice how the metal bars rise far above the wood bars. This visual comparison explains why a metal feels colder at room temperature. Pos 0.8's heat moves through solids mainly by conduction. Conduction occurs when particles collide and transfer energy. In metals, free electrons carry a large amount of heat. These electrons move quickly from the hot side to the cold side. In wood, only lattice vibrations phonons carry heat efficiently. Phonons travel slower and scatter more in a less ordered structure. Thus, a metal feels colder because its electrons conduct heat faster. The rapid energy transfer lowers the temperature of your hand quickly. Wood retains warmth longer because phonon transport is slower. This difference explains why a metal object feels colder than wood at room temperature. Pos 0.8's first. We compare the thermal conductivity of aluminum and pine. Aluminum conducts heat about 237 watts per meter Kelvin. Pine's conductivity is only around 0.12 watts per meter Kelvin. Next, density differences shape how much material stores heat. Aluminum weighs roughly 2,700 kilograms per cubic meter. Pine's density is about 450 kilograms per cubic meter. Specific heat tells us how much energy raises temperature. Aluminum's specific heat is 900 joules per kilogram Kelvin. Pine's specific heat is approximately 1,400 joules per kilogram Kelvin. Because aluminum transfers heat faster, it feels colder at the same room temperature. Pos 0.8's when you touch a metal plate, its surface feels colder than the room. This happens because heat flows from your skin into the metal faster than it can spread inside. The metal's high thermal conductivity allows energy to move quickly through its bulk. In contrast, wood conducts heat much slower, so less energy leaves your hand in the same time. After 10 seconds of contact, a temperature map shows a steep drop at the metal surface. The wooden block surface remains closer to room temperature because its internal heat transfer is sluggish. Thus, the bulk temperature of each material stays near ambient, but the surface temperatures differ. Your skin senses this difference as a feeling of cold on metal and warmth on wood. The visual overlay highlights these gradients, making invisible heat flow visible to learners. Understanding surface versus bulk temperature explains everyday sensations without invoking exotic physics. Pos 0.8's when a metal object touches skin, heat leaves the body quickly. Skin contains cold receptors that fire when temperature drops. These receptors are sensitive to rapid changes, not just absolute value. Metal's high thermal conductivity creates a steep temperature gradient at contact. The skin's surface cools faster than it can recover heat from deeper layers. Cold receptor spikes increase, sending signals to the brain that feel cold. Wood, with low conductivity, spreads heat slowly across the skin. Thus the temperature change at the surface is gentler and receptors fire less. The brain interprets this as a milder sensation, even though room temperature is identical. This explains why metal feels colder than wood under the same ambient conditions. Pause 0.8's infrared cameras record temperature as light in the far infrared. When a hand touches metal, heat flows rapidly away. The camera shows a sharp drop to about 20 C on the metal surface. In contrast, touching wood produces only a modest temperature change. The infrared image displays a gentle gradient, staying near 30 C. These color maps illustrate how thermal conductivity governs heat transfer speed. Metal's high conductivity allows heat to disperse quickly, keeping the skin cool. Wood's lower conductivity traps heat locally, making it feel warmer. The side-by-side footage lets students compare real-time data directly. Annotating temperature values reinforces quantitative understanding of thermal resistance. Pause 0.8's first. Place a metal spoon and a wooden block side by side on the table. Let both objects sit at room temperature for a minute so they reach equilibrium. Now, gently touch the metal with your fingertips and notice how quickly it feels cold. The metal conducts heat away from your skin faster than wood does. Next, touch the wooden block. It remains noticeably warmer for a longer moment. This difference arises because metals have higher thermal conductivity than most woods. Record your observations in a notebook. Note the time each material feels cool. You can also measure the temperature with a thermometer to confirm the numbers. Repeat the test with different metals and woods to see how conductivity changes. The experiment demonstrates that heat transfer is governed by material properties, not just ambient temperature. Pause 0.8's first. Remember that heat flows from warmer to cooler objects. The rate of flow depends on a material's thermal conductivity. Metals have high conductivity, so they transfer heat quickly. When you touch metal at room temperature, it draws your skin heat fast. Your hand feels colder because the metal is pulling warmth away. Wood, with low conductivity, resists that rapid heat loss. Thus a wooden object stays closer to your skin temperature. The sensation of cold is really about how fast heat moves, so the metal feels colder because it conducts heat away faster. Try touching different materials and notice the difference in warmth. Pause 0.8's metal feels colder because its high thermal conductivity pulls heat from your skin faster than wood, triggering cold receptors before the surface temperature changes noticeably.